I'm calling it. Starting the show, starting the recording. Hello, everybody. Happy Garbage Day. See, I'm wearing my merch today. It's a one of a kind. I'm the only person in the world who has Happy Garbage Day merch. It was a birthday present from my husband, actually. So, yes. So I wish you a happy Garbage Day, but not a happy anything else, because I'm not here for Valentine's Day. I am not. I waited tables all through college, and Valentine's Day was the worst day of the year to work. So I'm just begging you, anyone who is thinking about going out to dinner tonight, just don't. Okay, just eat at your houses. Save it for like Thursday when everyone's gone, and you will have a much better day. Everybody goes out to eat on Valentine's Day at the same time, and it's a disaster. So just don't. So that's my public service announcement for the day. So we are working our way towards a new topic here, logistic regression, our first instance of generalized models. Your homework 1, a review over general models and interaction terms in particular, is due Wednesday. Any last minute questions on that I can help with? Or pseudo last minute, I guess, depending on your definition? Not yet. So for those of you who are still working on it, and I know there's quite a few of you, because I peeked at the database to see how it was going, I would recommend that when you get to the last section, just to write down like on a piece of paper what the slope of experience is like for each group and just have it sitting in front of you to answer the questions. That way you don't have to keep scrolling back up to find where the numbers are. That will make it a lot easier to see the patterns. The same thing with the adjusted group means conditional on experience 4. If you just write out what those 4 numbers are, then it will make it easier to talk about how they're different and whether they're higher or lower, whether the slopes are stronger or weaker, that kind of thing. So that would be my one piece of advice based on the conversations I've had this far. I did release your next formative assessment, I believe number 2, is available inside ICON. You might be able to answer all of the questions at the end of today, but if not today, Thursday for sure. As just a reminder, those are 2 points for making an effort. You can be as wrong as you want to. I just want to encourage us to be able to keep up with the material in between assignments and have a chance for a structured review. I will let you know when your next homework is available, probably later this week. That will be due the following Monday, and it will be over logistic regression. So keeping in line here. So we did, just another public service announcement. We are forecasted to have snow again on Thursday. So if Iowa public schools are closed, I'm going to be calling it and having class only on Zoom. But I'm going to take the good laptop home to use that so we don't run into bandwidth problems. I figured out that it was the recorder specifically. So Friday morning, I re-recorded what we did in class on Thursday because I wasn't able to Zoom and record at the same time. But I'm taking the good laptop home, so I'm optimistic that Thursday will go better if we end up on the Zoom format, which is what I'm expecting. So, yay, February. We're all tired of winter, but it's not tired of us yet. So, what are you going to do? All right, any questions or things I'm forgetting to mention before we dive back into stuff? I think we got like 4 slides in, maybe 5. Should we just start over again? Does that make us happy? Yeah. Yeah, there's a term for that. It's not review. We call it re-go over. Like present it as if you've never heard it before. Re-go over. Happy to do so when necessary. So I'm on lecture 2 here from the top of the deck. So terminology, first off. The idea of what makes a generalized model different from a general model. The "ized" means not normal. So that's the first piece of what is changing is what we are assuming about the distribution of our outcome. Previously, we said that the leftover part of y, meaning the residual part, conditional, that's another synonym for that. The idea of leftover is conditional. That part is supposed to be normally distributed. But that's only a reasonable thing if your outcome is a continuous variable that has, a reasonably symmetric distribution to start with. If that's not a reasonable thing, then we pick another one. We just change our choice. So there are built-in distributions that work much better for other kinds of outcomes because they are ranged from the possible values that your outcome can have. For instance, the first type of outcome we're going to predict that is decidedly not normal is binary. Whether or not something happened. Very common type of outcome in a lot of contexts. Turns out there is a distribution for that. It's called Bernoulli. and it's a distribution of only 2 possible values. Likewise, if we're modeling a count of how many times something happened, there are built-in distributions for that, such as Poisson. What's interesting about those cases and many others, though, is that there's actually not residual variance as a concept in these distributions. There is no separately estimated variance, except in normal and very few others. So the way that we talk about effect size, the way that we think about how good our model is, has to change because we don't have this standard of how much variance did it explain. Why do we care? Standard errors. So the issue is that these standard errors for the things that you do care about, the effects of your predictors, those come from our model for the variance, this idea of what type of distribution. So if we pick the wrong one, then the inferences that we make about our effects are probably going to be suspect. So standard errors give us p-values. That means we might end up saying something is significant when we shouldn't, or vice versa. For those of you reading along with the Agresti book, that's one of the more technical options. And by the way, I got a question last week. Should I understand everything that's in that textbook? No. I don't even understand everything that's in that Agresti book. But I'm giving it because folks who are majoring in EMS and folks who want to become really skilled in this need to get used to seeing things written that way. It's definitely less acceptable. It's not acceptable, accessible, that's the word I wanted. It's definitely from a more technical perspective, but it balances out all the tutorials and example articles that I added to the reading list that kind of swing the opposite way. So do the best you can with the readings. If there's specific things you want to ask me about, let me know. But otherwise, I feel like it's my job to sort of distill the big picture of it and give it to you with examples. But the readings are there to flesh out the additional layers of complexity. But on that note, Agresti calls this aspect of what the conditional distribution should be a random component of the model. Now that's all well and good, but it is not a synonym for the term random effect, which is for those of you who are in the multi-level or longitudinal classes, that's different. That is not the same thing. Even though they use the term random, it's not the same. So just a disclaimer there. Second new piece of what makes a generalized model different is, well, if we're predicting an outcome that's not continuous, we need to make sure that our predictions obey the boundaries of what that outcome could possibly be. The way that we do that is something magical called a link function, which is a transformation. But a link function does not transform your data. When you do an analysis using these models on a binary outcome, it stays binary. It's still zeros and ones. What's going to happen behind the scenes is that the link function is going to translate the mean to be predicted into something that is more continuous and unbounded. The idea of taking it back to the original scale of the data is an inverse link. So link is going from the data up to something created by the model. Inverse link is coming back down. As an example, binary. The mean of a binary variable is computed in the exact same way as the mean of a regular variable. It's going to be the proportion of cases that have a 1. So that is your starting point for predicting a binary outcome. If you don't know anything else about a person, what's your best guess for an outcome? The mean. So let's say that you have 60% of your sample has a 1. Okay, the mean is 0.6. The possible values, though, for what that mean could be, the lowest it can be is 0 and the highest it can be is 1. In which case, if you're at either of those extremes, you don't have a variable, you have a constant, and this is not going to go well. But all predictions for what the probability is that someone would get a 1, which is really what we're talking about at this point, all predictions for the probability of a 1 have to stay within 0 and 1 as well. So the link function that we'll use for binary data needs to understand that the highest probability you can have is asymptotes at 1, and the lowest is at 0, and the link makes that happen. Likewise, for counts, we're going to use a different type of link called a log, the natural log. Logs are used to make sure that counts don't go negative. The lowest count you can have is 0. You can do something 0 times, but you can't do something negative 2 times. Doesn't work. And why you can think of ANOVA, regression, general linear models as still within this framework is if you say, well, my conditional distribution is normal, and my link function is something called identity. Identity is statistician for times 1. Identity means 1. I don't know if there's a special term for 0. I don't see that one, but identity is 1. So I gave you a real-life bummer of an identity link last time. This is an example scratch-off ticket from Christmas 2 years ago we spent in Hilton Head. This is a bingo ticket where you have to match the particular letter and number combinations out of the choices here on your card. I got a bingo right here. It was worth $10. This particular card promised bingo extra because you could multiply your winnings by some multiplicative factor, and I scratched it off and it says 1x, meaning identity link times 1, meaning I don't get any more money than the $10 I won. So this was a bummer of an identity link in my book. And yes, my family's like, why are you taking a picture of a scratch-off card on Christmas morning? Because I'm going to put it in my class, of course. That's the first thing I thought when I saw this. It's like, oh, this is a great example of an identity link. Okay, so once we have a distribution that makes more sense for the outcome and its possible values, once we have a way to turn the prediction into something that stays within the boundaries, then we're home free. Number 3 here, what's known as the linear predictor, and that's a fairly universal term in this context, is composed of the fixed effects of your predictors, the same as usual. It also is including the random effects for those of you who are interpolating this into a multi-level setting. Then we can talk about intercepts and slopes and how to talk about simple effects and interaction effects and all that stuff in the exact same words. A 1-unit change in x corresponds to this much change in y. The only catch is that it's not regular y, it's linked y, like it's in logit y or log y or whatever linked scale we're on. That's the only thing that has to change. The other little piece of this is that because of the way that these models are estimated, every term that you add to it is another burden in terms of estimation. So these models will break down if you try to stick a ton of predictors in them, and that would never happen in a general linear model as long as you've got degrees of freedom. Okay, how we doing? Am I talking too fast? A little bit? I'm feeling a little manic today, and I can't quite tell why, but sometimes I get that way. So what if we tried to predict the binary outcome with a general linear model? How could that go wrong? So if I'm predicting a binary outcome, what I'm actually trying to predict is the probability that any one case has the event happen to them, has a 1. So if I put together a model, say, that has x1 and x2 as predictors, then under this framework, I would say that beta 0 is my intercept. It's still the expected outcome when all the predictors are 0, but the expected outcome now is the probability of a 1. Likewise, beta 1 and beta 2 would talk about how the probability of a 1 changes per unit higher of x1 and x2. And E would be the difference. Whatever probability was predicted by the model, the linear predictor in red here, and what they actually got. So the model becomes the predicted probability of a 1 would be like the y hat part, and then E is whatever the difference is between what you actually got. Well, the first problem is the prediction itself. A linear model keeps going forever. The line created that links x and y is a straight line. That's fine if y is continuous, and it could conceivably vary all the way from the range of the variable from positive to negative infinity. However, in this case, we need to make the line shut off. We need to make sure that no matter how high x goes, the probability of a 1 doesn't go above 1, and the probability of a 1 doesn't go below 0. So this type of curve is what the link function creates. What's going to happen is that when we talk about how x predicts the link transformed y, it will still be a straight line. But when we inverse link, when we back translate that into probability, it's going to make this bendy line instead. So that has several implications for how we would talk about the effect of x, because the effect of x is not constant anymore. the effect of x is going to be the biggest around a probability of 50-50, and it's necessarily going to result in smaller and smaller changes to the probability as you get close to these boundaries. So here's our first link function, our best friend, the logit. Step 1, go from probability to a metric called odds. So odds is the probability of a 1 over the probability of a 0. So for instance, if my mean of my outcome is 0.7, that means 70% of the people got a 1, 30% got a 0. That would translate into 0.7 divided by 0.3, an odds of 2.33. If I flip it, if I have 0.3 divided by 0.7 instead, then the odds are 0.49. So odds is weird because it's asymmetric. It's bounded at 0, it goes into positive infinity. So some genius figured out that if we take the natural log of the odds, then we're cooking with gas. Then we have something we can predict. So this is our new friend logit, otherwise known as log odds. You can call it either one. As I mentioned, I think last time, I had a graduate student argue with me that because you take the log of it, this is the logit, not the logit. That sounds fine to me too. But the cool thing about logit is that it's symmetric. The value of the logit tells you the probability of a 1, and -1 times that tells you the probability of a 0. So 50-50 neutral probability is a logit of 0. The logit is higher as you move towards probability closer to 1, and the logit is lower, negative, as you move towards probability of 0. So the link then between the two, it can be depicted here. Probability is on the y-axis of this graph on slide 8, ranging from 0 to 1, and logit is on the x-axis, and logit ranges from positive to negative infinity. So a logit of 0 corresponds to a probability of 0.5. A logit of 0.9 corresponds, or excuse me, probability of 0.9 corresponds to logit of 2.2. 0.1 instead is negative 2.2, and this is where we ended last time, as I recall. Can you predict what a logit would be for 0.01 based on this table? Yeah, minus 4.6. So this is really handy because if you know immediately, if you know what the probability of a 1 is, you just flip it and you know what the probability of a 0 is. That is not true in odds, which is an asymmetric link. Here's another picture. So this is a different way of depicting the mapping of probabilities into logits. The top of this picture here is the probability metric ranging from 0 to 1. Ding dong, there we go. So probability of 0.5 corresponds to an odds of 1. So 0.5 divided by 0.5 is 1. Take the log of that, and that's a 0. So probability of 0.5 is logit of 0. A 1 unit change in logit from 0 to 1 has the biggest jump from 0.5 to 0.73. But every equal 1 unit change in logits from that point corresponds to smaller and smaller changes in probability. Logits go on forever and ever. The highest logit that, for instance, one of the packages I use to do analyses M+, it shuts it off at -15 and +15. Because at that point, you're like 0.9999999, whatever. So a 1 unit change in X is going to predict logit Y. And logits can go on forever and ever, so we don't have to worry about logits going out of bounds. But then when we back translate that logit into probability, the probabilities stay between 0 and 1 like they're supposed to. So back translate is what I keep saying. The technical term is inverse link. I also call it unlogit. So if you go from probability up to logits, that's a link. If you go back down from logits to probability, that's an inverse link or an unlogit. Okay, so that's one problem with predicting binary outcomes, is this idea that we can't go out of bounds. That's what link functions are for in a more general sense. Logit is one special case that we're talking about. The other problem pertains to the residuals. A general linear model would say that the residuals have some estimated variance that is constant. That cannot be true for binary data. So we go back to my little equation here. I have the predicted probability of a 1 from what's known as the linear predictor here, my fixed effects, beta 0, beta 1, and beta 2 working together to make some prediction. And then I compare that to what my y actually was. Y is either 0 or 1. Prediction is going to be somewhere in between the two, hopefully, and E is the difference. So each potential probability has an E that's either this far up or this far down. There's only two possibilities. You're either off in one direction because you got a 1, or you're off in the other direction because you got a 0. And how far off you are depends on how close the predicted probability is to 0. It's not constant. So residual variance can't possibly be constant all along y like it's supposed to be, because variance of a binary variable is dictated by the mean. The formula for variance is the proportion of 1s times the proportion of 0s. And here's what it would look like. Only at a probability of 0.5 would you have the maximum variance of 0.25, and as you move off of 0.5, the variance necessarily has to shrink until it becomes 0 if your mean is 1 or 0. So variance is not constant in these models. It can't be. The consequences of that for our inferences is that standard errors computed off of some kind of average variance would sometimes be too big and sometimes be too small. What we need is for the error to kind of stretch and shrink as it moves along this probability continuum. So we're not going to say that E is normally distributed with constant variance anymore. We're going to pick a new distribution for it, one that actually fits binary outcomes, our new friend Bernoulli. So the top of slide 11 here has univariate normal, just to remind you how ugly the formula is for that. This is the height of the data given the mean and the variance, because those are the two parameters that we need to figure out the height under a normal distribution. Bernoulli distribution, the formula is this little thing right here. It's the simplest one I know. It's the height of a 1, if that's what you got, or it's the height of a 0, if that's what you got. The end. If my data are binary, and I know that, say, 25% of the cases got a, let's see here. If I know that 25% of the cases got a 1, the blue one, then I know that 75% got a 0, the end. I don't need to compute a variance. It's known from this. So the Bernoulli distribution only has one parameter. We don't need to talk about residual variance because it's a function of the mean and it's a non-constant function. So here's what a model would look like then, applying our new best friend logit and all of its variations. So there are 4 different equations on this slide, right? They are the same thing. One of the difficulties that I've had in learning these models and trying to teach them is that different books talk about the same thing in different ways. And when I finally figured out that these were all the same, I was really like, what? How could you do this to me? So I just want to put it out there. They're all the same. The difference is in what is on the outcome side. So in generalized linear models, the hardest part of this is figuring out what the hell y is, because y can be 3 different things. It can be logits, it can be odds, or it can be probability. So logit is the log of the odds. So it's the probability of a 1 times 1 minus the probability of a 1. Otherwise, probability of a 1 over probability of a 0, log of that. If you're predicting logits, your linear model here looks the same as normal. Pun intended, right? Because it's normal distribution, same as normal. Yeah, see? They're like, yeah, stop, Lisa, I got it. Tough crowd. So this I prefer, because if I see this equation, I know what to do with it. Beta 0 is my expected outcome when x1 and x2 are 0. It's just the expected outcome is in logits. Beta 1 is the change in the logit for a 1 unit change in x. Done and done. So the model linearly predicts the logit if I have these linear effects of x1 and x2 just like usual. Cool. But then you're left with the problem of trying to explain what the hell a logit is. Yeah, shaking your head, exactly right. Well, what if I told you my logit was 1.5? Do you know what that means? No. Well, it's a positive number, so that means that my probability is above 0.5. If I told you that my logit was negative 1.5, it would be just as far away from 0.5 in the opposite direction, towards 0. But yeah, if you were to give people a set of predicted outcomes in logits or make a picture where logit is on the y-axis, no one will know what to do with that. Other than knowing that if the slope of beta 1 is positive, that means it's making the logit go up, which means higher x goes with more likely to have a 1. A negative slope means with higher x, you're more likely to have a 0. X goes up, y goes down. So the direction is just as informative, but the amounts are kind of weird because it's in this logit-like universe. So the solution to that, to some folks, is to say, all right, let's just take the log off and let's deal with this thing called odds. In odds, neutral is 1. You're just as likely to have something happen as to not have it happen. But then we have to exponentiate or unlog it into this. So this function, if you take the exp, e to the is what this means, and apply it to each of the terms, you would end up multiplying them together rather than adding them. And that just breaks my brain. I can't handle that. I just can't. So the odds middle ground here, some people find it useful to talk about odds and odds ratios, as we'll discuss in a minute, and to me, they will never make sense, ever. But they're very common, and I will teach you how to get them out of your software. So then if we skip the weird one in the middle here and come down to probability, to strip off the odds and the log changes the same exact expression into this. E to the model over 1 plus e to the model. So the part that's in parentheses here is the same as what you get directly if you're just predicting the logit. So this idea of going back from logits to probability, this is inverse link. The good news, everybody knows what a probability is. If I told you there's an 80% probability of snow on Thursday, you would know that I'm probably not going to have class. Here, I'll have it on Zoom. By the way, if you're stuck on campus, you can come into the room and Zoom from here. You can have class in here. I just won't be here. I will be being mommy at home, in addition to Dr. Lisa. For a while, he called me Dr. Mommy when he was 2. Which was, sort of cute and fun, but for whatever reason, he absolutely would not say Dr. Daddy. He refused. Mommy's a doctor, not Daddy. We're both doctors, actually, but whatever. So yes, I will be Dr. Mommy on Thursday with 80% chance. You would know what that means, like 80% probability. If I tell you that the probability of you winning the lottery is, 0.00000000001, you would know what that means, right? Not in your favor. So the good news with probability is that people know what that means. It's an outcome that has direct meaning in everyday life. You can make a picture and show the predicted probability of this happening or that happening. The bad news is then what the hell do I do with my model? I can't talk about any of these coefficients with any of the usual language. It is not the expected outcome, beta 0. It is not the effect of x, on the outcome. Like none of the intercept slope language that you're used to works. So my preferred way to tackle this problem is to interpret the coefficients in the logit metric where we know what to talk about with the slope, but then to help people understand the impact of those logits on probability. So I would generate like a table of predicted probabilities or a picture of predicted probabilities from the model. I would not give them predicted logits because no one knows what to do with that. Last but not least, you can shortcut this formula and its redundancy in the numerator and the denominator by changing it into this one. The only catch is the minus 1 here. So you can say 1 over 1 plus e to the not logit, -1 times the total prediction. So I have a couple Excel files where I've worked out predictions just to demonstrate how this stuff works, and I often do it this way because it's less typing. So all three of these would lead to the same conclusions, but the difference is in the metric of why we're talking about. Logits are continuous and symmetric. 0 is the midpoint for 50-50 probability. Odds are only continuous in the positive direction. They stop at 0, and the neutral point in odds is 1, and probability is bounded on both sides, and the neutral point is 0.5. Okay, how are we doing? Nodding? Those of you who knew what a logit was, is this sounding familiar? Maybe? Okay. So logits are everywhere. It's not just in these models, but if you head into latent variable measurement models, item response theory models, item factor analysis models, like if you want to do a factor analysis on binary outcomes, logits are in there too. So this is a very important concept to move forward with as you build in models with complexity. If you're ever going to predict a binary outcome in any kind of model, you need a link on it. So here's a table that will help, I think, clarify what you can do and what you can't do with respect to inverse linking model parameters and predictions. So if I were to compute a predicted outcome, say for somebody with this value of x1 and this value of x2, I can come up with a predicted outcome. We're still going to call that y hat for right now. Cool. Y hat and logits, not helpful. So I can take that predicted outcome and I can move across the three metrics all I want. If I take the logit and I exponentiate it, I unlogit it, e to the predicted outcome, that becomes odds. Then I have the odds of a 1 divided by, or basically the probability of a 1 over the probability of a 0 gives me a number that's odds. Cool. If you want to take that even further into probability, fine by me. Then it's e to the prediction over 1 plus e to the prediction, and then you're in probability. So once you have a predicted outcome, you can freely move in and out of these three metrics all you want. You cannot do the same for the slopes. This is like the number one thing I see people screw up at first, so I'm getting out in front of it. Beta 1 is the change in the logit for a 1 unit change in x1. Cool. Beta 2, change in the logit for a 1 unit change in x2. Cool. I can take that beta 1 slope and unlogit it into something called an odds ratio, e to the slope, e to the beta 1 or e to the beta 2. Those are something called odds ratios, and those are effect sizes for the slopes. I hate them, but they're everywhere. That is totally fine to take a logit slope, exponentiate it back into odds. What you cannot do is move one layer down. You cannot take a slope and somehow convert it into talking about a change in probability. It does not work. The reason that it does not work is coming back to this picture right here. The change in probability depends on where you are on probability. It is not constant, it's bendy. So there is no way to take a logit slope and change it into the change in the probability instead, because it will be smaller the closer you get to 1 or 0, and it will be biggest in the middle. So if you want to talk about probability, the order of operations is use the slope to compute a predicted outcome in logits, then take that predicted outcome and move it down into probability. We can only slide up and down the metrics on the outcome, not on the slopes. Okay. How we doing? Okay-ish? All right, do you want to see some examples, or do you want to talk a little more about binary and other link functions? I can go either way on this one. One vote for keep talking about more choices for binary, or numbers? One vote for one. One vote for examples. Okay, I need a tiebreaker. Examples? Examples have it. Okay, we'll come back to this then, because there's a couple other links that I want to show you. But Logit is the main one. Logit is by far the most common and the easiest to work with. Okay, so I'm going to pick up then example 2a. Got some numbers for you. The original files that have the data, the syntax, and the output in Stata, R, and SAS, even though it's not in the handout, are inside a zip folder next to this handout. So you can have all the original files and scroll through those outputs directly. I have this annotated so that we can look at the syntax and the results without having to run things live. So these data came from this website I borrowed. I'm pretty sure they're fake based on the fact that it's exactly 400 people and the proportions that we have. The original story of this was predicting an ordinal outcome for how likely a college student was to apply to graduate school, where there was 3 choices of 0, 1, or 2. They didn't say what that meant, so I gave up my own labels. For the sake of this example, though, I collapsed that variable into binary. Just to make this example, not recommending that in life, just because I didn't have a binary outcome that was readily available. So I collapsed this variable into 0 means no, I'm not applying to graduate school. And either 1 or 2, I'm calling pry, which is the Midwestern slang for probably. I'm probably going to apply to graduate school, but probably not. That's what that means. Probably is also an accepted alternative. Probably is too long to say.
What about prawly?
Probably also accepted. That I think is a little more southern in origin.
I'm from Missouri.
Missouri, oh, that's...
No, I say Missouri, though.
Okay, yeah, no, I'm from Missouri.
Oh.
I was born in St. Joseph, which is northern.
No way.
Way.
That's where I'm from.
Oh my goodness. Yeah, some of my family still lives in St. Joseph. I lived there till I was 7. Or St. Joe, as it's called to the locals. So, way. Yes, my grandmother said it was Missouri. It's Missouri to me, but there's a dividing line somewhere where it switches to up. But probably would be from Missouri. Pry, I think, or probably would be from Missouri. But anyway, that's what that means. The predictors that I have here are undergraduate GPA, which is on a 4-point scale. I'm going to center that at 3. Whether or not at least one of their parents has a graduate degree, which is a binary predictor, and whether the student attended a private university. So 1 continuous predictor, 2 binary predictors. I have some notes about what I'm using here. You can read that at your wish. So to make the data then, nothing too exciting other than the transformations that I needed to make this. So first data code and then R code. The first thing that tells me this is fake data is they didn't have an ID variable. Never see a real data set that doesn't have an ID variable for who's who. So I made one. In Stata, there's a gen function that's _n by which you can do this. I'm creating an outcome called out of apply, that's apply 3 and apply 2. That way we can keep track of what the outcome is we're predicting, since there's 2 versions of it. So apply 2 is what we're going to work with today. So if apply originally was 0, I'm giving it a 0. If it was greater than 0 originally, I'm giving it a 1. So just collapsing it there. I'm renaming my predictors and changing it so that the slopes are going to be positive, so that the odds ratios are going to be easier to interpret. So parent ed is what they had. I'm calling this pair D for degree. GPA I centered at 3, since a GPA of 0 is not possible. It's probably possible, but not in people who are going to grad school. And private, I changed from the public and fixed it. So public used to be 1, now it's private is going to be 1. Labeling the variables as good hygiene and subsetting my data set to only the cases that are complete, because the program's going to do that for you anyway. In R, I have the packages that I'm using here. This one's just going to be GLM, which is a base function, and a couple of extra ones that I downloaded for extra pieces of that. So I'm reading in Excel data in R. I made an ID variable with this little function that I found online. Then I make the 3 version, the 2 version, center and rename my predictors, switch public to private. Here's the labels that are not in the data set, by the way. That's one thing that's weird about R to me, is that if you try to label your variables, sometimes it won't run analyses as a function of that. So I've gotten used to just putting the labels as comments. That way at least they're part of the syntax file. And then subsetting to just complete cases on the variables we're interested in. So descriptive statistics, always first. But in predicting binary outcomes, this is going to be especially important to help you figure out what your software is doing. Some software defaults to predicting the 0. Some software defaults to predicting the 1. So that's the first thing that we'll have to do is figure out which way is up with respect to our prediction. Key to figuring that out is knowing what the proportion is of people who have a 1 versus a 0. So here's the range of the variables that I have. The 3 predictors here, 2 are binary, 1 is continuous GPA. And then apply 2 is the binary 0-1 outcome with a mean of 0.45. So that tells me that 45% of the respondents have a 1 and 55% have a 0. That means that the first model that I'm going to have here, empty model, better give me this probability back. If the empty model gives me something other than this, either there's some problem with my data or it's going backwards. Okay, questions on the setup or the code? Yeah.
Can you explain the codes like the complete pieces?
Yes.
What does the 5 and 9 mean?
Those are the what column number I'm selecting for completeness on. So it was columns 5 through 9 of the data set that I say, if they are incomplete, then get rid of them.
Okay. So it depends on the data you put in.
This would only work in this particular data set. Otherwise, you'd have to have the numbers here with like a C list for that, or the names, I mean, rather than the numbers. This is just a little bit shorter.
Yeah, if you don't have missing data, then this code doesn't matter.
It won't do anything. But in these models, like if you start with a model that has some predictors and then you add cases that have like other predictors and some of them are missing, it changes your sample. And that means that some of the things we're going to do to compare whether we've improved the model aren't valid. So we have to have the samples be exactly the same across all the analyses to make comparisons. All right, did you have a question in the back?
Is that the data that your columns are your excluding them?
This is basically saying keep the people that are complete on these columns 5 to 9. So if they're gone, if they're not complete, they won't get put back into the data set. So I'm basically renaming it, dropping the.
Have all those columns.
Yeah, so if I wanted to have multiple versions, I'd have to come up with a new name over here that would be like the subset of the original example too. Okay, other syntax questions? All right, here's your very first model. An empty model. Remember what empty means? No predictors. Why am I doing this? To figure out if my model is predicting the 1 or the 0. That's why. So it's not just pedagogy, it's actually what I would do in life if I'm using an unfamiliar package and I don't know which way it's going. So translating then my notation, the log of apply to is my outcome variable equals 1 over apply to equals 0. This is the log of the odds, and I'm going to abbreviate that as logit apply to equals 1. So that's my way of saying this is what we're predicting is the log odds. The only thing that's in the model right now, beta 0, just an intercept. It's empty. So what I should get back is the mean of my outcome in logits. That won't do me a bit of good until I turn that thing into a probability. So e to the beta 0 over 1 plus e to the beta 0 is how I get back into probability. That's the inverse link. The good news is that you shall not get your calculators out for any of this. The code will do it for you. You don't have to compute this stuff. Every package has a way to do it more or less in a algorithmic fashion. So here's Stata code first and then R code second. Logit is the command that I'm using in Stata. That command is only for binary outcomes. So in Stata, there's separate routines for different types of models. So this means a logistic regression with a logit link and a Bernoulli conditional distribution. That's what we've ordered here. Apply to is the outcome. Comma separates out the options, and no log means don't print the iteration history, so it cleans up the output just a little bit. log likelihood is the first number that we see right here, and that will show up in R as well. That number is the height of the data under the current model parameters. In the direction of log likelihood, bigger is better, taller is better. So we're going to be paying attention to this number as an indication of how good our model is at predicting this outcome. It also serves a more convenient purpose from the perspective of homework. This number times -2 is going to be the first thing that I ask you for the rest of the semester about any model. Why -2? Because that's how we do model comparisons. We haven't talked about that yet. But here's -2 times that number. That's the next little piece of code that I have in here. This number tells you right away if you have the right model in terms of its contents. It's analogous to what the residual variance was used for in your first homework. So it's kind of like a unique identifier for your data and your model. It only has meaning relative to other models for the same data. So I can't look at -275 and make any kind of conclusion about that. But I can compare that to what happens to it after we add predictors and see how much taller the predictors made the log likelihood. So the only model parameter that I care about right now, this thing right here, the constant, which is what? What does _const mean, data users? What's my word for this? Yeah, the beta zero fixed intercept. Yes. Yes, indeed. The intercept is -0.2. Well, that's interesting since the values are only zeros and ones. How do I get a negative intercept? The intercept is supposed to be the expected outcome when all my predictors are 0. I don't have predictors, so this is just the expected outcome, which should be the mean. How did I get a negative value for a mean of a binary variable? The answer is on the page. This is not the mean of a binary variable. It's the mean in logits. Logits. Now I know this is negative. That means the mean is less than 0.5. But I can't do the math in my head to figure out exactly what it is. We're going to do that math in just a second. Yes, it is in logits. So your model parameters are in logits. You cannot talk about probability or zeros and ones directly. They are in logits. Information criteria is the next table. We haven't talked about that yet, but these are other ways of judging how good your model is relative to alternatives. Here's the magical translation to get from logits back into probabilities. In Stata, the command is just margins. So margins is used to compute predicted outcomes. In these models, it's guessing. I'm guessing you're going to want probability with this. So if I take e to the intercept in logits, which is the -0.2, over 1 plus e to the intercept in logits, that gets me to 0.45, which is exactly the number that's given down here in my output. 0.45 is a number we've already seen. That was the proportion of cases that have a 1. So what this is telling me is that the model is predicting the logit of having a 1 as the outcome, not the logit of a 0. If that number had turned out to be 0.55 instead, I'd know the model was predicting the 0. This matters for interpreting everything else that follows. As x goes up, what happens to y? Does it go up or does it go down? If the model is predicting the 0, then everything is logically backwards from what we're used to thinking about. So this helps me establish what is being predicted. In R, then, same process, same equations. I'm using GLM, which stands for Generalized Linear Model, not General Linear Model, which is only a special case. Family is how I tell it what kind of model I want this to be. So GLM is a much more general, like has more choices to it, not just logistic regression, but lots of other kinds. So I'm saying binomial and link equals logit. Bernoulli is a special case of binomial when there's only two. Or there's only one option, one trial of two choices. Let's put it that way. That's why it's binomial. We'll talk about binomial more generally when we talk about predicting proportions. And link equals logit as opposed to other choices. Formula then is how I tell it my equation. Apply to is my outcome variable. Squiggle 1, meaning just one intercept, please. Coefficients then, the intercept is the same -2 because it's in logits. In terms of the height of the data, it's given to you as log likelihood times -2 because that's what we'll need to do to it to compare models. So it's anticipating that and trying to help you out. AIC and BIC are transformations of log likelihood that indicate model goodness. We haven't talked about those yet, so we'll skip them. And last but not least, to back translate that predicted logit for the intercept into probability, for now I'm doing the math manually. So 1 over 1 plus e to the -1, and then the coefficients from that. So that is an example of using, let me find it again, this bottom formula right there. That's what I just wrote in R, to go from logits to probabilities. Coefficients is the stored object inside this model too. So then I'm asking for it to be printed, and lo and behold, the number that shows up is 0.45. So now I know which way is up. We're predicting the 1, which is that they are at least somewhat likely to decide to go to graduate school. Any of that you want to hear again or hear differently? Question? Yes.
Can you explain how you know whether it's predicting the 1 or the 0 again, please?
I will. I know that with 2 pieces of information and just asking for descriptive statistics. The mean of this 0-1 binary variable is 0.45. That tells me that 0.45 has a 1 and 0.55 has a 0. In an empty model, all I have is an intercept, which is the expected outcome for everybody, which is the mean. So this expected outcome is in logits. When it comes back to us, that's the -0.2. When I unlogit it back down to probability, e to the logit over 1 plus e to the logit, that turns into 0.45. So the mean of the variable in probability is 0.45, which matches the mean of the original variable. Does that help? Not yet. Okay, fair. I appreciate your honesty. Basically, this number could only be one of 2 things. It was either going to turn out to be 0.45 or 0.55. If it's 0.45, I know that the model is predicting the mean of a 1 instead of a 0. Did you have a question? Or you want to help?
So, like in Stata and R, like, I don't know, a lot of times with Stata, like, there are defaults, right? And so, like, is this something that is, like, sort of the default for it, and this is more of, like, a teaching sort of thing where you need to, like, it's important to understand and be sure that you're oriented properly within your program, or is this something that is like, no, you literally have to do this because it could be different every time. You need to make sure that, like, I have no idea with R. Like, maybe in R you have to, like, tell it exactly what you want or you won't get it. But Stata has a lot of default sort of things, so I didn't know, like, where it fell in that.
Okay, so the question was, like, would I need to do this in life, or is this just a pedagogical exercise and a data orientation exercise? The answer depends on your package. So once you are familiar with the package, like once you've learned that logit predicts the 1, in Stata, you would not need to go through this empty model process. However, this piece is why I say it that way. Because Stata, as part of its default output, is going to do a model comparison using the log likelihood from this model as a baseline against which to compare more complex models. In R, this does not get spit out for you. So in order to have this baseline against which to compare more complex models in R, I need to know what the log likelihood is of this empty model. So for that reason, even after I know what the package is doing, I need that number. And so I'll have to estimate this model to get that number. Okay. Yes.
And how you know your R model is predicting y equals 1 or 0 because you didn't get the description data out of the R?
Well, I didn't print it, but it's right here. So
Okay.
they would basically be like this table, but less well, with a bunch of extra columns because I'm using the describe function. So yes, this idea of orienting yourself to what it's predicting is actually really important when we get to categorical data models. Then it really is, it becomes very tricky to figure out what is happening by default or sort of on an assumed level, and reproducing the frequencies table with your model is like step 1 to making sure you understand what it's doing. And that is true on all the packages for categorical. But because IB was a SAS user who had to pick up Stata and then more recently picking up R, like this is literally what I do to make sure that I understand what something is happening as I run it in the program I'm familiar with, and then I make sure that the output matches. So it's pedagogical for me for these purposes, but I do think that there are situations in which the model's complicated enough that just fitting an empty model to get your bearings is a useful exercise. More questions?
So if beta 0 or the mean was like about 0.51, it would be towards 1. If it's less, it would be towards 0.
Yes, so in this data, 0.45 is the proportion of cases that have a 1, 0.55 is the portion that has a 0. So if what Stata was doing by default was predicting the 0 instead, the logit of having a 0 is the outcome, then this logit coefficient that is negative 0.2 would be positive 0.2 instead. Because logits are symmetric about 0. So because it's negative 0.2, that back translates into a probability of 0.45. That means that the model is predicting the probability of a 1. If this logit was 0.2 instead, negative 1 times this, that would back translate into a probability of 0.55, and then I'd know that it was predicting the logit of being a 0, of not having something happen. So it's up to you what you're calling the 0 and the 1. So I just had a consultation with someone the other day where they were interested in predicting who was going to drop out of a treatment study. And because the analysis was who is going to be not likely to complete it, the 1 was the dropouts. That was what they wanted to know, was the likelihood of dropping out. Somebody else could take the same data set and say, no, I want to know who's likely to complete it, and the completers would be the 1. But all of your slopes are going to talk about the probability of something as x goes up. Your first job is to figure out what it is the probability of. What makes generalized models tricky is working across all of these different outcome scales, the logits and the odds and the probabilities. The X predictor part works the same as usual. Okay, do you want to see another model? Maybe? Just a couple slopes? No interactions yet? Okay, so now we know what weighs up. We are predicting the logit of someone's choice to apply to graduate school. So here's my new model with 3 predictors. GPA for an undergraduate centered at 3. Whether or not at least one parent has a graduate degree, and whether they went to a private university. So I throw those 3 predictors into my row here after the outcome in Logit. Outcome's always first, predictors are next. And one other piece here that we haven't talked about yet is storing the results of this analysis in terms of the log likelihood so we can do a comparison down the road. So our new log likelihood is minus 2.64. Relative to the previous model, it was minus 275. It's higher, less negative. So we're heading in the right direction. We've improved our model by adding these predictors. Great. Let's see what happened a little more specifically. So, coefficient, synonym for estimate. Standard error, inconsistency of that estimate across samples. Z, this is new. What letter is usually there? T. Guess what? This column is computed the exact same way, whether it's labeled T or Z. Its coefficient divided by standard error is this thing. The question is whether this test statistic, as it is known, this is a Wald test, univariate Wald test because it's for each slope. The question is whether you are trying to figure out where 0.05 is on a T distribution or a Z distribution. The difference is denominator degrees of freedom. So this is assuming that sample size doesn't matter. That is a Stata limitation. That is also an R limitation. That is not a SAS limitation. SAS has denominator degrees of freedom that you can use in smaller samples. So if you have a very small sample, you are more likely to make type 1 errors potentially because of this, in the same way that we switch from Z to T for everything else. But this is the probability given a Z distribution as the reference, and confidence intervals as well. So first, at the bottom, unfortunately, my constant. That's my intercept. What is the definition of an intercept always without respect to logits or anything else? Expected outcome for what? When the predictors are 0. Guess what? It still is. No matter what you're doing, that is the definition of an intercept. The only catch is what's outcome and what's predictors. This is the expected outcome in logits. The logit is minus 0.54 for what kind of reference person? Someone with a GPA of 3, whose parents do not have graduate degrees, and who went to public university instead of private. Now, a logit of minus 0.5 tells us that that reference person has a probability lower than 50-50 because it's negative. Beyond that, I can't get more specific. It's negative, though. That means probability is less than 0.5. The rest of these predictor slopes are positive. That means the logit of a 1 increases as you move up on these predictors. These are positive slopes. That means the probability of having a 1 is higher the more x you have for each of these. So the direction stays the same. A positive slope is as x goes up, y goes up. A negative slope is as x goes up, y goes down. Here, y goes up means more likely to have a 1. Y goes down means more likely to have a 0. So if I look at the GPA slope, for instance, for every unit higher GPA, the logit of applying to graduate school is higher by 0.55, significantly so. So people who did better at school would like to stay in school, sort of makes sense. The last two predictors here are binary predictors. So this is whether or not at least one parent has a graduate degree. If they do, your logit of applying to graduate school goes up by 1, significantly. This one refers to public versus private university. If you went to private university, your logit is higher by 0.2, but not significantly. So the only switch in the way that I'm thinking and talking about this is logit goes up, not y goes up. It's in the logit metric, which is continuous and goes on forever and ever. So I can keep talking about the logit going up and up and up and up as I move up on x, and it's no problem. Okay. Model fit stuff. Haven't talked about this yet. Margins. I asked for predicted outcomes for hypothetical people to make a point. So I'm asking for predictions from a GPA of -1 in units of 1 up to 1, which translates into a GPA of 2, 3, or 4. And I'm holding the other predictors constant at 0. An option you probably haven't seen yet, Stata users, predict XB, means predicted in the logit metric, in the linked metric. So somebody who has a GPA of 2 has a predicted logit of -1. A logit is -0.5 if their GPA is 3, which is what was given by the model intercept. And their logit is about 0 if they have a GPA of 4. The reason that I printed this is to make this point. These 3 rows correspond to a 1 unit change in x. The difference from this number to that one is 0.548. The difference from here to here is another 0.548. It's a linear effect of GPA on the logit. So for every unit higher GPA, logit changes by that much, yes.
Is that because it's like centered at 2, so it's the same on either side, but like as you went further out, that number would diminish, or would it stay the same the whole time?
It would stay the same. I could predict the logit for a GPA of 10, and it would just be 0.548 each increment, because in logits, the slope is linear, just like we're used to. The interpretation of the slope is a constant change in the outcome for a 1 unit per unit change, but it's in logit outcome. But then you're like, what the hell is a logit? So if you take the predict XB off and you run the same code, now it's in probability. So the probability of someone with a GPA of 2 applying to graduate school is 0.25. The probability of someone with a GPA of 3 is 0.37. And the probability of someone with a GPA of 4 is 0.50. The difference between those numbers is not constant. The difference is 0.11, 0.13. So the difference in probability per unit GPA is not a constant number. It's that S-shaped bendy function where the biggest differences are going to be in the middle and the differences sort of shut off as you move toward the edges. So where people fall into trouble with this is like, okay, so here's my slope in logits, it's 0.548. Now what if I take that slope and I try to put it into probability? Like e to this number over e to that number, that would translate into a slope of 0.39. That number means nothing. Because the change in probability for a 1 unit change in GPA is not 0.389 and it's not constant. So you cannot convert a logit slope into something of probability. That is the rule. You cannot convert the slope. What I did instead is convert the predicted outcome from the slope. The results of the slope you can convert. So order of operations. First get a predicted outcome in logits, then take that down to probability. You use your slopes to get the predicted outcome in logits in the first place. All right. This is fun, isn't it? Yeah, kinda. Anything when it's the first time is strange and weird and uncomfortable. But this is the first time you're seeing this idea of transforming Y into something different than what you started with. So the transformation is happening behind the scenes through the logit. All of this is machinery designed to make sure that at the end of the day, predicted probabilities for everyone in your data set stay within 0 and 1. That's what it's for. All right, questions? Or anything that you need me to say again? Or slowlier? Then the last piece of table here, and I'll let you go. In stata still for the time being, and then we'll look at R next time. I wrote the same code again with 2 little letters on the option, OR. You would think that means, or what? No, it means odds ratio. This is translating those slopes rather than predicting logits into predicting odds. E to the slope is what this table is giving you, as noted out here. These slopes are now considered effect sizes in this world. Odds ratios is what these are called. We'll talk more about where those numbers come from. But they tell you what the expected change in the odds is per unit GPA, but it's in multiplied. Like the odds increase by this much as a factor. I can't handle these. I can't. They don't mean anything to me. I can tell you that an odds ratio of 1 corresponds to a slope of 0. A positive slope will have an odds ratio between 1 and positive infinity, but a negative slope has an odds ratio between 0 and 1. So all of negative effect sizes get shoved into 0 and 1, but positive effect sizes can range from 1 to infinity. And that asymmetry just bugs the hell out of me. So whenever possible, I would change my model so that I'm expecting a positive slope, so that I don't have to deal with odds ratios less than 1, because those numbers get compressed into something that's meaningless. But these are your effect sizes. So you have to rerun the analysis with this option. There's no way that I could tell to get everything from one run. But they're helpful in trying to label this, not as coefficient, but it labels it as odds ratio, so that you know what you're looking at least. All right. 315, we made it. Yes, it's okay now. You can look up. I'm going to stop talking any minute, I promise. Thank you for being here. Let me know if you need anything as you're working on finishing your homework for Wednesday nights. Office hours tomorrow for me. Otherwise, I hope to see everybody Thursday. Happy Garbage Day.